Hello everyone, I'm Chen-Wei from National Yangming Jiao-Tong University. Today, I'm honored to present our research work, GCC, Generative Color Constancy via Diffusing a Color Tracker and CVPR 2025. This research is a collaboration with MediaTek, exploring how to leverage diffusion model to solve color constancy problems. First, let me briefly introduce what color constancy is. When we have an image with color cast, color constancy is to remove this color cast to make the image appear as if captured under neutral white light. The left image shows the original image affected by lighting conditions, while the right image has been corrected through computational color constancy to present more neutral colors. This is a crucial component in the image signal processing pipeline. In traditional photography workflows, professional photographers must physically carry color trackers to the shooting location, as shown in the image. They need to place a standard color tracker in the scene, and capture photos containing this tracker. After capturing the image, the software then extracts color information from various patches of the tracker and performs white-balance correlation as shown in the workflow. However, this entire pipeline is too complex. This led us to think, can we leverage existing generative models to accomplish this task more efficiently and eliminate the need for physical color trackers? Based on these motivations, we propose the GCC method. Unlike traditional workflows, our method can directly generate virtual color trackers in the scene. The flow was as follows. First, we start with an input image. Then we pass any color tracker download from the internet onto the image. After processing through our GCC system, we obtain a harmonized tracker that adapts to the scene lightning. Since the tracker position is predetermined by us, we can directly sample color patch from the generated tracker to perform white balance correlation. This completely eliminates the need to physically carry color trackers while achieving automatically color constancy correlation. Our method is inspired by diffusion line from CVPR 2024. However, traditional diffusion model approaches have several key issues. First, they require multiple inference passes for ensemble averaging, which is computationally inefficient. Second, there's a trade-off with noise strength. Insufficient noise fails to effectively suppress original color information, while excessive noise disrupts structural consistency. Third, stochastic noise leads to non-deterministic output. In contrast, our approach is fast, stable, deterministic, requires only a single inverse to obtain consistent results. Next, let me detail our training pipeline. Our method is based on fine-tuning the stable diffusion tool in painting model. Our input consists of the input image and a color tracker position mask. We apply color jittering in the mask region to simulate the inconsistency between neutral color tracker and color cast background image that we will encounter during testing. Next, we build a Laplacian pyramid to extract high-frequency components from the input latent representation. This step serves two purposes. First, preserving the structural detail of the color tracker while minimizing the influence of the low-frequency color information. Second, encourage the model to focus on harmonizing with scene illumination rather than simple reconstruction. Finally, we decode the latent output and calculate L2 loss against the ground truth. The entire training process uses an end-to-end approach, ensuring that the generated color tracker accurately reflects the ambient lighting condition of the scene. Now, let's move to our inference pipeline. During inference, there are two main differences from training. First, we don't need to calculate loss. Second, instead of mass color jittering, we directly pass a neutral tracker onto the input image. Then, following the same pipeline as training, we obtain the output image. Finally, we can sample color patches from the generated tracker to get the file illumination estimate for white balance correlation. This table shows cross camera evaluation results, which is an important challenge in the color constancy field because different cameras have different spectral sensitive characteristics. We perform cross evaluation between the NUSA and Gala datasets, train on NUSA and evaluation on Gala, and vice versa. The result shows that our method achieves competitive performance, especially in worst-case scenarios demonstrating the robustness of our approach. Traditional color constancy methods typically assume single global illumination, but real-world scenes often contain multiple light sources. Our method can naturally extend to handle spatially varying illumination conditions. The zero-shot evaluation results on the LSNI dataset demonstrate that our method is comparable to existing approaches across different lighting scenarios. Finally, let's look at some visualization results. The key point here is that our method can place tracker at any position in the scene and obtain stable, consistent results in single illuminated scenarios. The left image shows our generated color trackers that blend well into the scene and reflect the corresponding lighting conditions. The right scatter plot shows our estimate illumination values compared to the ground truth. You can see that our estimates consistently cluster near ground truth, demonstrating that our accuracy and stability of our method. Thank you for your attention. For more details, please feel free to check out our project page and paper through the QR codes.